Welcome everyone. Welcome back to another BGCSE past paper review. Today we're reviewing a physics paper and it is a paper 3 from the year 2021. Please remember to write your school number, also write your candidate number and your surname along with your initials. Today I'm reviewing section A, and so you'll see the link or the clickable icon up to your top of your screen at the end of this video for section B. So you can look out for that. Also, please remember to read through instructions before you start the examination. And if you have any question or any queries, please clarify those with your examiner. Also, they are being very generous and really nice to present to you a formula sheet. So you have a formula sheet to work with. You may need some of these formulas. You may not use some of them. All right, so let's jump into our first question. All right, and the first question reads that a crane on a mailboat lifts cars from the dock onto the boat and into the storage compartment of the vessel. A crane makes lifting work easier because because of its mechanical advantage, which is MA. So give the formula for MA. So mechanical advantage is calculated as, so let's give you a number of formulas. It could be 1, let me just say MA equals to the output force over the input force. All right, it can also be given as the load over effort as well. So let's make a note of that. Is also can be calculated as load over effort. All right, so the same thing, output, which is based on the load, and the input, which is based upon the effort. All right, another formula that you can use to calculate efficiency is the input distance, or the distance moved by the effort. So it can also be given as the input distance, which is the distance moved by the effort, input distance, divided by the output distance. All right, so you have 3 different ways which you can actually write the formula for mechanical advantage. Let's go to the next part of the question. The next part of the question here reads, which is part B. You see a car of mass 700 kg is lifted 5 meters into the air by a crane in 10 seconds. The electrical supplied to the crane is 5 kilowatts. Calculate the efficiency of the crane. All right, so there are a number of things we need to figure out right here before we actually go into the efficiency. But let me give you the efficiency formula first that we're going to use. And then we break down the question a little bit further. So the efficiency that we're going to use here is the formula for efficiency is equal to the power output. So we're going to have power output over the power input. All right, and you can also look at the formula sheet for the appropriate formulas as well. And all of this will be multiplied by 100%. Okay, so I'm going to put here multiplied by 100%. So all of this will be multiplied by 100%. All right, so multiplied by 100%. All right, good. Now, once we have that formula, now what we can do is now break down the question in terms of power. And just to make a note that power is equal to, to find power, it is equal to the work over time. So power is definitely work over time. Power equals to work divided by time. All right. Also, it could be energy over time as well, which is change of energy over time. All right. Also, if you want to find the formula for work, the formula for work is, so work is equal to force times distance, just to make a note of that. All right, so we have those 3 possible formulas there that we're going to use in this question. All right, so let's look at the different power. So we can look at the power input. And the power input based on the question here is our 5 kilowatts, okay? And remember that 5 kilowatts is the same thing as 5,000 watts. All right, so let's look at the power output, and it's based upon the car or the load. And so here we have a mass, but the formula for work does not include mass. It includes a force, as I said, FD. So to change the mass into a force, which is weight, okay, so we're going to find the weight of the car. So the weight of the car here will be, so weight of car, let's just make the weight of car equals to, I'm just breaking down this as best as possible, is equal to 700 kg multiplied by 10. We're going to take gravity to be 10. And so that's going to equal to 7,000 newtons. That's the weight of the car. Now, once we have the weight of the car, what you can find now is the power output. So the power output equals to, again, power is equal to work over time. And so work is equal to force times distance. We're going to say the force, which is 7,000. So we're going to say 7,000 multiplied by, sorry, this is actually, 7,000, which is the weight here. So 7,000 multiplied by 5, which is the distance that it moves, divided by time, and that time is 10 seconds. So the power is going to be work, which is the force, which is 7,000, multiplied that by 5 meters, which is the distance, and all of this will be divided by, let's say all of this divided by time. And so the time given there is 10. So this divided by 10. All right, and so if that divided by 10, what you'll get there, you will get 3,500. So it's going to be 3,500 watts. A matter of fact, what you can do is also calculate this in kilowatts. So this is also, if you divide by 1,000, what you get is 3.5 kilowatts. All right, so that's our power output. Now, our power input, as we established there, was our 5 kilowatts. So now we can find the efficiency by using the formula, the power output over power input multiplied by 100%. And so just to make a note that you can either use the kilowatt units or you could use the watt units. It doesn't matter. Once you keep both at the same units, you will get your correct answer. So our efficiency now is equal to our power output, which is our 3.5. So that's going to be 3.5 kilowatts. I'm using the kilowatts. Again, if you use the wattage, which would be 3,500, and you divide it by the input power, which is going to be 5 kilowatts. Again, you could use the 5,000 watts. So it could be 3,500 over 5,000. You get the same answer. All of this again multiplied by 100%. And what you should get here when you do this is equal to 70%. So that will be the efficiency of the machine. All right. So again, it's power output over power input. And the power output is based upon what you're lifting, which is the load. And so that is of the car. And then the power input will be that of the crane that is actually doing the work. All right. So let's look at part C. And part C is asked to identify 2 factors that can affect the efficiency of the crane. And so when you think about the crane has moving parts. So definitely one of them could have been friction. So let's say friction could be 1. Okay, so friction is 1. What else we can have as affecting the efficiency? And when we talk about affecting the efficiency, you're actually talking about what cause it to lose some energy or lose some power. And let's just say friction because of the moving parts. I'm just put here moving parts in brackets. So the friction is caused by moving parts or due to moving parts. Another possibility right here also could be because of heat. So let's just put that and say heat. And the heat is generated again is because of the thermal design of the crane. So because of thermal design. because some cranes may designed to lose less heat compared to other cranes, right? Another possibility too, if you think about it, we can talk about the resistance, air resistance. So air resistance could be another one. And point to note again is that some days may be more windy than others. So therefore the crane may work against the wind on some day more than other days. Okay, so let's say air resistance. All right, and again, this is also based upon wind for one. It could be based upon wind that just generally against the wind going upwards or against air going upwards. Another possibility here again could have been resistance in electrical wires, because remember, if you're supplying electrical current, then the resistance in the wire, so resistance in the wires. All right, and of course, if you have a smaller wires, then definitely you have more resistance to the current. And if you have less current flowing, then of course you're going to affect your power output as well. Bigger or thicker wires will have less resistance. Shorter wires also have less resistance. So there are a number of factors that could affect that. Also remember that the crane also gives off a lot of sound. So energy could be lost because of sound as well. So I could even put that one, because cranes really is that most times they are noisy. So you could lose energy by sound. Okay. So loss of energy by sound or noise. Okay. So you can lose energy because of those stuff. All right. So friction is generally one of the first things you should think of. And also air resistance, definitely heat. All right. And so resistance in wires and sound, those are really things to think about secondarily. But yeah, they are good answers that you can actually apply to the question. All right, now for part D of this question, it said the cable breaks and the car falls into the sea. The car does not sink right away. It said draw a simple force diagram to illustrate the forces acting on the car, and it's a correctly label each force. And this is, I think, it worth, let me see the amount of marks. 2 marks. So it's 2 marks question. So just need to, it's a simple diagram. Matter of fact, it asks you to draw. All right, and so let me just quickly outline something. The first thing I'm going to do is to, let's say this is a car. So this will be the car right here. All right, and the car will be, let's just draw a simple box to represent the car. Okay, you don't need to draw a car itself, just a box to represent the car. And the car will be in the water, so just put some scribble lines to represent the water. And then you're gonna have a force pushing upwards, and these must be straight lines, must be nice and straight. All right, another one is pushing downwards in the opposite direction to that one that's going up straight. So generally, these will be in the central part of the object. And so here, let me just type in this. It will be the buoyant force, and that is generated because of the water. So this will be the buoyant force. The buoyant force. All right, and it could be, you could put FB, uppercase F and a subscript B as well. And the one that going down here is the weight of the car. And the weight of a car, you can also put in bracket for weight. It is mg, so you can put mg in bracket. All right, so you can put mg there. All right, so that will be our simple force diagram representing the 2 forces, and we properly label them. All right, and let's go to the next part of the question. And this will be the last part because it's saying 10 marks, total of 10 marks. So it said, explain why a pulley is an example of a simple machine. So a pulley is a simple machine because it has very few moving parts. Okay. It has very few moving parts. I remember that's actually what defines a simple machine. A simple machine has very few to no moving parts. All right. All right. So that's end question number 1. Let's quickly go into question number 2. And in question number 2, I think I'm moving a little bit too fast out of script. All right, so this is question number 2. And question number 2 here, it is based up on force, pressure, and Hooke's law. And right here, it is saying that now figure 2.1 is a solid metal block which rests on a desk. The weight of the block is 70 newtons. I want to make note of that. Let me just highlight that. 70 newton is going to be very important for us, because when we talk about force, pressure, Hooke's law, then yeah, the weight is going to be important. And its dimension here is 25 centimeters by 11 centimeters by 14 centimeters. All right, so we're going to see how that is applicable here. All right, let me just go a little bit, minimize a little bit here. All right, just to make sure that we get all the papers together. All right, so we are good to go. And so what we're going to do now is to look what they actually asked us to calculate. And the first thing here said that based on the orientation. So based on the orientation, calculate the maximum pressure in Newton per centimeter square exerted by the block on the surface of the desk. So it said based on the orientation. So I want you to be careful with this question. It's based on the orientation. Based on how it is positioned now. We're going to calculate the maximum pressure exerted on the desk. And I want to make a note right here that this part is rest on the desk right now. It is a 1225 by 14. That's a side of the block that is rest on the desk. However, as you know that the most pressure will be created by the smaller side, okay, or the smaller area, because the smaller the area is, the greater the pressure. So the 14 by the 11 will generate the maximum amount of pressure possible by the block, but it didn't ask the maximum pressure created by the block. It said the maximum pressure based on the current orientation, so based on the orientation that is exerted on the desk. But what I'm going to do, I'm going to calculate both of them, and so you see how I work through this. So based on what they're asking us, if you look at the dimension here, and again, just to make a note that pressure, all right, so pressure is equal to the force over area. So force divided by area. All right, and so our force, as in stated in the question, was 70 newtons. But let's look at our area based on the orientation. Based on the orientation of the block, our area will be 25 centimeters by 14 centimeters. All right, so let's quickly just write that out. So let's say force F equals to 70 newtons. So we already have that. And our area equals to, that will be 25, which is the largest side, multiplied by 14. All right. And so that will equal to 350 centimeters square. Okay. And so our answer now in terms of pressure, so let's say P pressure equals to the force, which is 70 divided by our 350, and that equals to 0.2 0.2 newtons per centimeters. Okay, so let's put cm square. All right, but as I said, I'm going to show you the maximum possible pressure that can be generated by or created by the block. And so the smallest area, remember the smallest area will give the greatest what? Pressure. So the smallest dimension on this block is the 14 by the 11. Okay, so I'm going to write that out for you quickly. And this is not what the question actually asks. You know, so it asks based on the orientation. And so just make a note right here. So I'm just putting that there. So here now the pressure would have been equal to the force. Let me find the area first. So area would be equal to 14 multiplied by 11. And that equals to 154 centimeters square. All right. And so the pressure, the maximum possible pressure by the block would now have been 70 divided by 154, which equals to 0.45 newtons per centimeter square. All right, so that's the maximum pressure that is possible, can be created by the block. But based on the orientation, the maximum pressure here is 0.2. All right, so just to make a note of that. All right, let's just jump on to our next question, or next part of the question actually. And it said, liquid of pressure, identify two factors that influence pressure in a liquid. And an easy way to kind of figure this out is based on the formula for liquid pressure, okay? And the formula for liquid pressure, let me just put it on top right here. Matter of fact, let me put it at the bottom right here. So the formula for liquid pressure is actually equals to density of the liquid multiplied by its mass, mgh. All right, so now there are two things that actually matters in terms of the pressure, because the mass of the liquid will be constant, that will remain the same. The gravity acting on the liquid will be the same, provided it's on the same planet or on the earth at the same altitude. Then the gravitational force will be the same, the mass will be the same, but the two things that can change is the density of the liquid and also the height, which is the depth. So the two things here that will change the pressure of a liquid is, one is density. So let's put one here as density. The density will change it and can affect it. Or the other one will be, of course, the depth. So how deep is a liquid, or greatness in terms of volume, right? All right, so definitely those are the two factors that can affect the pressure within a liquid. Jumping on to the next part of the question here, and this one say that part C is a hooks. It's a hook of negligible mass is inserted into the metal block to allow it to be suspended from a 15 centimeter spring, spiral spring, as shown in figure 2.2. And let me just quickly analyze this question here. And it's based on this diagram. So based on this diagram, we know a few things. And let's just quickly put in those few things. Or matter of fact, I like the important stuff right here. We have our 15 centimeter, which is a spring with nothing on it, if you notice that. And then when you put on this block, it increases to 28 centimeters. Now, what you want to also point out is the same block that we're working with. So this block here is 70 kg. Okay, no, 70 Newton actually. All right, so the block is 70 Newton. It's the same block that we just talked about. All right, from the previous question. I'll just go back in the question. I will show you that just to make sure you remember. All right, so notice right here that we highlighted earlier, that the block is 70 newtons. It's the same block they're referring to here. All right, so we have our weight of the block. We have this two different length in terms of spring. And so what we can make a note right here in terms of, we have two different length. So we're going to have our length 1 and length 2. So the two different lengths will provide us with the actual extension. So the actual extension of this spring based on this weight or this block is actually equals to 28 minus the original length, which is 15, and that equals to 13 centimeters. So the extension there is 13 centimeters. Just make a note of that, just in case we need it after this, all right? So that's very important to note. All right, it said, given that Hooke's law is obeyed, calculate the force constant of the spring. All right, so calculate the force constant. First, let us point out a formula that we need to use to do this. So force is equal to the constant multiplied by the extension. All right, so force is equal to KE. Now, to find the constant based on this formula, so we know that constant here would have been equal to the force divided by the extension. We already calculate the extension up top, thank God. All right, so what we're going to do here now is divide our force, which is the 70 Newton, by your extension. So this is going to be equal to now. So the constant here will equal to our 70 Newtons divided by our 13 centimeters. And that will give us here 5.38 newtons per centimeters. All right. So that is our constant of this spring. All right. So let's go to the next part of the question. It said the total length of the spring, and you have to calculate here the total length of the spring when another metal of weight 300 newtons is extended from the same spring. So it's not saying add this to what was there before. It said when this is now extended from the same spring. All right. So now we know what the constant is. All right. And so what we're going to do now, again, we're going to find extension in this time. And now we have our new weight or force. So based on the formula, we know that extension would have now been the force divided by the constant. All right? That would be our extension, the force divided by the constant. And so the force that we're working here with now, we're going to be 300 newtons divided by the constant that we calculated earlier, which is 5.38. And now, as a result, this will equal to 55.76 centimeters. Okay? So it'll be centimeters. Now, what I want to point out, based on the constant, it extends that. However, we need to account for the original length of the spring. Do you remember what the original length of the spring is? And they ask us here for total length of the spring. So we need to know the original length of the spring. All right. And so the original length of the spring here is 15. So that's 15 is the original length. All right. So we're going to add 15 to that extension. Okay. So if the extension is 55.6, then we're going to find total length. Let's say total length equals to our 55.76 plus our 15 centimeters, and that equals to 70.76. All right, centimeters. That will be overall length of the spring, which is the extension based on the 300 newtons plus the original length of the spring, which is 15. All right, so let's look at part D now. Now, part D, it asks us to sketch an extension against force graph. So it's extension against force graph. They actually label the graph for us, which is nice. All right, for a spring stretch beyond its elastic limit. So since I put extension on the y-axis and force on the x-axis, then you have to be mindful of how this will curve. And this is, again, that extend beyond its elastic limit. So what you're going to have first and foremost, you're going to have a line. So what you're going to have is a straight line to indicate that it's obeying Hooke's law first. So it's the line of proportionality. And then because it now extend beyond its elastic limit, what you're going to do now is just to kind of create a curve kind of line. Mine a little bit too curved towards the left, so yours is not going to be that curve out. Let me just take that out and then put it back in better. All right, so you're going to come something more like that. Right. Yep. Awesome. All right, so that will be our graph. Our graph will appear like that. All right, and again, just to make a note that right here will now be our elastic limit. So elastic limit will be somewhere where the lines start to curve. So it'll be somewhere right here. So this is now our elastic limit. Okay, you can just make a note of that. Our elastic limit. Let me write that down. All right, so make a note. So this is now our elastic limit. All right, I think I jump off the page. All right, then let's put it back. Right, it says elastic limit right here. All right, cool. All right, so now we are finished with that. So let's go to the next part of the question. Now, matter of fact, this is the last part of that question. This is the total right there. All right, so we're on the next question. It's question 3, and we have one more question after this. And so question 3 now, we said this question is about energy. All right, so all of us like a little bit of energy, right? Now, it said figure 3.1 shows a simplified diagram of a hot water heater. It said, which has an inner tank and an outer case with a thick layer of insulation between. Now we said the heater rated at 360 watt is used to heat water when in operation. Now, based upon this, let me just go down a little bit here. You have first you have cold water going in from the bottom, you have hot water going out in the top, you have the login or insulation on the outer case, which is here, which is the inner case, and then you have the heater element. So this is what going to apply heat to the water inside. All right, and this is electrically operated. But there's something important here that they mentioned here, that we have 3,360 watt. That's very important, yeah? So let's make a note of that before we go into anything else. Just remember that. It said, name the method of heat transfer occurring in the tank as the water is heated. So as the water is heated, the warmer particles due to kinetic energy will go to the top, and then the colder ones, or the one with less kinetic energy, will fall to the bottom. So the higher energy ones will rise, the low energy one will fall, and a consistent falling and rising will lead to what they call boiling, and boiling is due to convection. Right. This is lead to convection. So it's all due to kinetic energy. All right. All right. I remember that kinetic energy is kind of proportional to, well, not even kind of, it is proportional to the temperature. So the more higher the temperature, the higher the kinetic energy. All right. So part 2 here now is said, and it said minimized by the use of plug-in insulation, and it's actually name. So name here, the method of heat transfer that minimized by log-in insulation. That's actually what they're asking us. So we're going to name the method of heat transfer that minimize the use of the log-in insulation. That is actually radiation. So it prevents radiation, okay? So radiation is minimized by the log-in or insulated material. All right, so let's go to the next part of the question here now. It said that part B1, it said the surface of the outer case is shiny. State how this helps to reduce heat loss. So if the outside case is shiny, what it will do, it will reflect heat, or it will reflect radiated heat. So let's say it reflects radiation or reflects heat. So it reflects heat. All right, and let's put radiation in bracket. All right, or radiated heat, if you want to say that, radiated heat. So while reflect radiated heat, let's say reflect radiated heat, keeping heat in, right, and prevent, keeping heat in and prevents outside radiation as well. So whatever is on the outside stays on the outside, what is inside stays on the inside, okay? And prevents outside radiation. All right, so keep the heat in and prevent so there's no mixture of both temperatures, what is inside and what is on the outside. So there's no heat transfer. All right, so there's no heat transfer at all. All right, so let's make a note. So it reduces heat transfer, reducing heat transfer. All right, so it reduces heat transfer. And remember, heat is transferred from hotter objects to colder objects. So what is inside will be maintained, because if what is on the outside is being reflected, then there's no possibility of transferring heat from one object to the next. All right, and that's the purpose for the insulation right there. All right, so for part 2, it said if the heater element was painted black, what impact would this have on the overall temperature of the water? And so if you painted it black, what will happen here? It will reduce the effect or the overall temperature of the water. So it will be reduced. And that's a 1 mark question. And just to make a note why it will reduce it is because since it's black, what's going to happen, it will absorb. So it will absorb, just to make an explanation right here, it will absorb some of the heat. Let's put some, okay, not all. It will absorb, let's say it will absorb some of the heat, okay? All right, rather than giving off all of it, all right? All right, so yeah, so the definitely the temperature will reduce because it if it's dark, then it would absorb some amount of heat itself, and then not all of it will be given off. So the efficiency will be reduced. In other words, all right. So for part C of this question, now we say that the heater is used for 10 hours. So let's make a note of this. I just like to make sure I light all of these important information. So we use it for 10 hours each week. For each week, the heater is used for 10 hours. And the cost of electricity here in the Bahamas here is 31 cents per kilowatt hour. Just to make a note as that as well. It said find the energy consumed each week. And if you want to find the energy consumed each week based on this information here, let me just go up a little bit more so we have enough space to work with. All right, so first to point out, right, is that here the heater itself is, just to go back to the previous question, because if you go back to the previous question, remember, it said that it used for, I'm going to show you the power. Let me just go back here so at least you have a notation of it. All right, so the heater here, which is very important, I think I highlighted it earlier, that the heater itself is rated 3,360 watt. That's very important. That's a wattage there. So the power output of the heater is 3,360 watts. We're going to use that in this calculation. Just make a note. So the power is, let's put it right here, is 3,360 watt. All right, it's also equivalent to, in terms of kilowatt, this is also equivalent to 3.36 kilowatt. Okay, so that's the wattage there in terms of kilowatt. Now remember, we need to find the kilowatt hours. And so the kilowatt hours here, let's put it on this line, will be the 3.36. We're going to multiply that now by 10 hours because it's 10 hours it used for 10 hours each week. Multiply by 10. All right, so that will give us here now 3.6 kilowatts. So that's the amount of energy consumed each week in kilowatts hours. Sorry, kilowatts hours. Let's put the hours there, right? So that is our value in terms of the energy consumed. Now we say, what is the cost of that energy to the Bahamian consumer? So the cost of that energy, remember, for every kilowatt hour, it is 30 cents. So we're going to multiply that now by 31 cents, not 30 cents, but 31 cents. So you're going to say 33.6 kilowatt hours multiplied by 31 cents. All right. And so what we'll get here, that will equal to 1,041.6, yeah, 0.6 cents. All right. So that is in cents. However, if we divide this by 100, then that will equals to, let me say R. All right, so or that will equal to $10. That equal to $10, $10.42. Okay, so in terms of cents, is 1,041.6 cents, or you get $10.42. All right, so that is the cost right there. All right, so let's look at part D. It said, water normally boils at 100 degrees Celsius. Identify two factors that can cause the boiling point of water to vary. And so one of the basic things that could change the boiling point of water is simple impurities, okay? So impurities is one of the major things. And example, you can have salt or dissolved minerals. So salts or dissolved minerals, whichever one you want to put. But impurities is fine. Another one here could be the altitude. Okay, and altitude will change the boiling point of water as well, because again, because as altitude changes, then the air pressure also changes, and that will also affect how the convection actually takes place. And so here again, another possibility here is also air pressure, okay, which is kind of tied into altitude as well. Okay, so air pressure will also affect it. So if you're at sea level versus a high altitude, then definitely the air pressure will be different, and it will affect the boiling point of the water. All right, because remember, as water boils, it creates a force as well, right? So if air is pressing against the water, then it would affect how these particles will actually move. All right, and also how much heat is transferred to each of the particles as well. All right, so let's go to question number 4. This is the last question for this section. And again, I'll put the clickable icon or link somewhere on the top of the screen for you to click and watch section B. All right, so in question number 4 now, we said the question is on electrostatic and electricity. It said during a thunderstorm, lightning and thunder are produced. Explain how lightning is produced electrostatically. And so lightning works with this is that so let's say lightning is formed. All right, let's say it is formed. It is formed when charged clouds pass over oppositely charged clouds. And not just oppositely charged clouds alone, but also the earth as well, all right? Over oppositely charged clouds or the earth. Okay, because again, the earth will also have a charge, and so they have oppositely charge, creating what they call here now, creating, I think I make a mistake right there, yeah, creating a great attraction. So this great attraction here now, creating a great attraction, giving off sparks, okay? Giving off or producing sparks. And so this sparks that is given off is what is called lightning. So the difference in charge, because remember, based on electrostatic, charges are generated by either by losing or gaining of electrons. So one cloud may become positively charged and next one may become negatively charged because they lose electrons. And while passing over each other, all right, then it will create that spark, all right, and then definitely going to get the lightning effect. All right, so part B is that during a lightning flash, a total charge of 52 coulombs flow. I said the average current is 2,600 amps. Calculate the duration of the flash in seconds. Now, based upon this, what you need to know are the useful formula to use right here is going to be Q equals to IT, which is current times time, okay? So Q is equal to IT, which is Q is the charge in coulombs, I is current in amperes, and T is time in seconds. Now, very importantly, in the question, we already have our current, which is 2,600 amperes, which is I. We also have our time here. No, not time, but our charge, which is 52 coulombs. So all we need to do now is find time. So time, based on the formula, time now would equal to the charge, which is coulomb, the charge divided by the current. All right, Q divided by I. And so the charge that we know here, it is 52. So it's going to be 52 divided by 2,600. All right, and 52 divided by 2,600 equals to 0.02 seconds. All right, that's really fast. All right, so that's how quick the effect will be, how fast it will travel. Okay. All right, so, or the duration of a flash. All right, for the next question here, it says, as a result of a lightning strike, the generators in the power station trip offline. Each diesel generator is rated 500 kilowatts. So let's label that as 500 kilowatts. All right, it said if the voltage of the electricity produced is 460 volts, what is the value of the current? I want to find current. Okay, so here now we have power, we have voltage, and we need to find current. Now what we need to do is to find a useful formula now that contains power, voltage, and current. Now, the form that is most appropriate for this question is going to be P equals to IV. So it is power is equal to current times voltage. All right. And so here now we can find our current. And so current I now would equal to the power divided by the voltage. Okay. All right. But let's look at power in itself. Power is given here as 500 kilowatts is same thing as 5,000 watts. So kilo is 1,000, so it's 500,000 watts. Okay. So what we can have here now as the formula for power is going to be as again 500,000. So 3 more zeros, 500,000 divided by 460, which is our voltage, and that equals to that is divided that 1086.96. Yeah, 0.96. This is in amperes. So it's 1086.96 amperes. Okay. All right. So that's now part C. Let's go into the next part of the question here now. It says sometimes during a power outage, there is a surge of electricity in the grid system. Explain how electrical appliances in the home get damaged due to electrical surges. All right, so this is a 2-point question. So we must quickly write down some information here. And so generally though, for you to have an electrical surge, it is generally whenever a large amount of current, but the large amount of current is experienced normally when the power is restored, or a sudden restoration of it, or when it is lost. Because when it's lost, they can have a quick build-up of current, and also when you restore it, you can also have a quick build-up of the current as well. So let us start about that. When the power, let's give you the outline of this one. The power is restored. An electrical surge can occur, which is a sudden, let's put sudden, which is a sudden increase in voltage. And this is generally in voltage, let's say above the normal, right? It's above the normal. It says normally above the normal. All right. And so this results in I current now. So this is where the I current part now come in. So this result in high current. Right. And also heat will generate it sometimes, and heat, right? Resulting in damages. So the high current or the high heat that is generated will damage the components, right? Resulting in damages to components. All right. If you have a fuse that can handle or can break, then yeah, the fuse may protect the components. But generally, surge will affect the smaller components first and burn them out. All right, because of high current, because the current is above the normal rating, and so because of that high current, it burn out those components and then it becomes damaged. All right, so this is the last part of this question here. It said, name one safety device that can be used in the home to protect electrical appliances and systems. So the very basic one here is beakers, okay? Breakers, I said beakers just now, breakers. All right, so you have breakers, you have surge protectors. You may buy surge protectors. Some are better than some, of course. Surge protectors. All right, and in some cases, you may have some main fuse, okay? So you can have fuse as well. Let me just say fuse. All right, so yeah, but the general one protect appliances in the home will be breakers. All right, last question. No, we finished with that question. We are section B now. All right, so again, I'm going to put the link or the clickable icon on top of the screen for section B. All right, and again, enjoy. Good luck on the exam. Look out for section B shortly.